Hybrid orbitals are objective number 3 in our current unit of study. This is what we'll take a look at in this video clip. The purpose of hybrid orbitals is this is a theory and modeling scheme that's used to explain observed bonding and geometries of molecules. So it's something that's used to help us explain things that have been observed with the shapes and bonding arrangements of molecules. Let's start and consider, specifically to molecules, what exactly is a covalent bond. A covalent bond is specifically when we have the sharing of two valence electrons between two bonding atoms, where each bonding atom contributes one electron to share in creating that covalent bond. For example, let's consider the molecule HF. A Lewis dot structure of hydrogen shows hydrogen with one valence electron and shows fluorine with 7 valence electrons. If we get overlap of the orbitals where hydrogen's electron cloud overlaps with the electron cloud of fluorine, we end up having this area where a pair of electrons is being shared by the two atoms, and this pair of electrons being shared between the two atoms would be what we would consider and call a covalent bond. Each atom contributed one electron to share, and it creates a pair of electrons being held between the two nuclei of the two atoms, and we have a bond between the two atoms known as a covalent bond. The need for the hybrid orbital modeling scheme for bonding arrangements around molecules can be shown using a molecule we're familiar with, such as methane. We know that methane exists. We know that methane's formula is CH4, and we know that methane has the 4 hydrogens singly bonded to the central carbon atom. However, in taking a look at the valence electrons of carbon, it can be seen that carbon has only 2 unpaired electrons. Based on this valence electron arrangement, carbon can make only 2 covalent bonds, one bond with each unpaired electron. So this valence arrangement of electrons for the carbon atom does not agree with what we see for a known structure of the methane molecule. This brought to rise a need for some other model to explain the bonding arrangements in molecules. And it's the development of the hybrid orbital scheme that reconciles our difference with what we see in the valence electron arrangement of a carbon atom and what we know to be the case of the molecular bonding arrangement in a methane molecule and other molecules. First, let's use an analogy to somewhat illustrate the concept of hybrid orbitals. Let's start our analogy by saying we have 4 equal cups of milk. 1 cup that's chocolate milk, 3 cups that are containing white milk. To add to our analogy now, we have a blender. We're going to place into the blender all 4 cups of milk, 1 chocolate cup and 3 white cups of milk, to give us a total of 4 cups of milk inside the blender. We run the blender for a moment, stop the blender, and now scoop out of the blender 4 cups of milk. When we scoop out the cups, we will no longer have a single cup of chocolate and 3 cups of white milk, but rather we'll have something where we have 4 cups that are equivalent mixture, where each cup will now contain an equivalent mixture of 1 part chocolate milk, 3 parts white milk. They're no longer white milk anymore, nor are they chocolate milk, but rather a blend, a little bit of chocolate and 3 parts white. And these are now equal and similar. They've been essentially hybridized, a blending of the chocolate and white milk. Now we're going to keep our blender, but now let's look at our orbitals that we have for our carbon atom. And we're going to hybridize or blend these orbitals to make a bonding arrangement that can explain what we see in molecules such as methane. We're going to place into the blender 1 s orbital, 1, 2, 3 p orbitals are going to go into the blender. Run the blender for a moment, pause. Now when we remove the orbitals from the blender, we're no longer going to have separate 2p and 2s orbitals, but rather what comes out of the blender now is 4 equivalent orbitals, where each orbital is 1 part s and 3 parts p. The orbitals are no longer known as s and p, but because they're a blending, they're now known as sp3. The sp3 designation tells us that the hybrid orbital is 1 part s and made of 3 parts p, and it creates 4 equivalent orbitals that are all the same, a blending, if you will, of the s's and p orbitals to make these new hybrid orbitals used in the making of a molecule. So our carbon atom with its hybrid orbitals has 4 equivalent sp3 orbitals. As we place our 4 valence electrons in, we need to follow Hund's rule, placing electrons singly in each orbital. With the hybrid orbital scheme, carbon now has 1, 2, 3, 4 unpaired electrons, so it has the capacity with the hybrid orbital scheme to make 4 covalent bonds. 4 covalent bonds is what we see and know to be the case in a methane molecule, so we now have an orbital scheme that agrees with what we observe for the formation and structure of a methane molecule. This is the utility of the hybrid orbital theory and modeling scheme with molecules. Now there's several hybrid orbital schemes possible. The molecule, when we do a Lewis structure, that's what ends up determines what the hybrid scheme needed to build whatever the molecular structure is that's indicated by the Lewis structure. For example, the hybrid scheme sp3 that's made of 1 part s and 3 parts p in the hybridizing creates 4 equivalent orbitals to be used in the creation of a molecule. Another hybrid scheme is known as sp2. sp2 is a hybrid scheme that's 1 part s and 2 parts p that have been blended together. The sp2 hybrid scheme would be utilized whenever 3 equivalent orbitals are necessary to construct the molecule as observed in our Lewis structures. Some of the hybrid schemes around the central atom include sp, which makes 2 equivalent orbitals around the central atom, sp2 that will create 3 equivalent orbitals, sp3 which can create 4 equivalent orbitals around the central atom. There's 2 more hybrid schemes, sp3d, which is for 5 equivalent orbitals around the central atom, and sp3d2, which creates 6 equivalent orbitals around the central atom. These last 2 hybrid schemes are used for when we violate the octet around the central atom in our Lewis structures. And this hybrid scheme, unlike the others, is only possible when the central atom is at n equals 3 or higher for the energy level of the central atom. Reason for this is if we look at n equals 2 for our energy level, the only sublevels that exist are s and p sublevels. With no d sublevel at n equals 2, it's not possible to bring a d orbital in and blend it with the valence shell electrons, since d orbitals do not exist when the valence shell electrons are at n equals 2. So this sp3d is not possible at energy level 2, only 3 and above. If we look at n equals 3, d orbitals exist at n equals 3, therefore making it possible for d orbitals to be brought into the hybrid scheme around a central atom. Since the d orbitals exist at n equals 3 or higher, the hybrid schemes sp3d and sp3d2 are possible with central atoms where n equals 3 or higher, and those are the only atoms that can violate the octet around the central atom in their bonding scheme. Let's do a couple examples of how we can utilize a molecule and Lewis structure to determine the hybrid scheme around the central atom. This is the goal of objective number 3 on our learning objectives for the unit. Once drawing our Lewis structure, the first part of our strategy is to identify how many things are around the central atom. Things around the central atom would be the number of atoms attached to the central atom plus any unshared pairs of electrons. Both atoms and unshared pairs require hybrid orbitals to hold them to the central atom nucleus. If we look at our water molecule Lewis structure, we have a hydrogen atom that's one thing, a second hydrogen atom that's two things, we have an unshared pair of electrons, that's three things, we have another unshared pair of electrons, that's four things. The number of things attached to our central atom in water is 4. Our next step is to find out how many equivalent orbitals do we need around the central atom. The number of orbitals needed is equal to the number of things attached to the central atom. So in this case, our number of things is 4, the number of orbitals we need is also 4. Central atom hybrid scheme, if we need 4 orbitals, that's going to be an sp3, would provide 4 equivalent orbitals around our central atom to make the bonding necessary to create our molecule. The way we can identify this is sp3 tells us, again, we have 1 part s, 3 parts p. Those pieces hybridize to create 4 equivalent bonding orbitals, or hybrid orbitals that we have. Let's do another example, the molecule SO3. The Lewis structure for SO3, we have 1 oxygen atom, another oxygen atom for 2 things, and a third oxygen atom, which gives us 3 things around the central atom in SO3. 3 things around the central atom means we're going to need 3 equivalent orbitals around the central atom. 3 equivalent orbitals are provided by the hybrid orbital scheme sp2. sp2 being 1 part s, 2 parts p. When hybridized, that creates 3 equivalent orbitals which we'll need for creating our molecule. Let's do one more example, the molecule astatine trifluoride. Here's our Lewis structure for astatine trifluoride. We have 1 fluorine atom for 1 thing, an unshared pair for 2, another unshared pair for 3, another fluorine atom for 4, another fluorine atom for 5, so we have 5 things attached to our central astatine atom in our structure. 5 things mean we're going to need 5 equivalent orbitals around the central bonding atom. 5 equivalent orbitals are provided by the hybrid scheme sp3d, and that would be the hybrid scheme required on the central atom in our astatine trifluoride molecule.